So we are going to talk more about limits today. So I'm going to do a quick review of a couple of things just to remind you how we worked with limits. So for example, so originally when we took limits, what we were looking for is being able to substitute numbers directly in to get the answer. So in this situation, we would take it and we would plug in a 1 anywhere there was an x, and that value would give us the limit. So we'd have 2 times 1 minus the 3. So you get 1 plus 2 minus 3, and the entire value then would give us 0, right? Totally legal, totally good. Okay, so now what we had is we ran into the problem where, for instance, if we had a problem now that was rational, it had situations where sometimes the problem could not be solved using a limit without manipulating the problem. So for instance here, if I have x minus 1 on the bottom, then this problem, when I go to substitute directly in, I get a 0 in the denominator. If there's a 0 in the denominator, then that means that it is undefined. So we can't find the limit that way. So instead we had to move on to then trying getting it simplified so that we could take the limit. So for instance, this factors out as an x plus 3 and an x minus 1. So we could factor things and see that, oh, well, this can be removed. That's a removable discontinuity. And so then we were left with the limit of x plus 3, and we knew that we could then substitute in and do 1 plus 3, and this limit is 4. Okay, so both of these situations, this is kind of what we worked on a lot, right, is going through trying direct substitution, then trying simplifying. After that, we went to graphing. Well, L'Hopital's rule gives us another strategy for solving when they don't work out, another trick. So L'Hopital's rule tells us if we have a limit in indeterminate form with the type of 0 over 0 or infinity over infinity. So what that means is that when you take the limit, the answer is 0 in the denominator, but if it's also 0 in the numerator, it tells us that there's a problem, that there's something that you can fix. And we talked about that a little when we did limits, is that that's kind of a key indicator if the limit is 0 over 0, that there's more that you can do to solve it. So then if this is the case, then the limit of the quotient of the functions is equal to the limit of the quotient of their derivatives. Okay, so for example, let's use this example that we already have here. When we take the limit, if we tried taking the limit of the given function that I first started with, this x squared plus 2x minus 3. We can also, just showing that this works with this problem, because when we substitute in a 1, we get 0 over 0. Okay, so there's that indeterminate form. So what this is saying now is that we can take this function, since this doesn't work, but it tells us we can do something. And L'Hopital's rule tells us we can take this top function and we can find the derivative of it. So we're going to take the limit as x approaches 1 of the derivative of this, which is 2x plus 2, over the derivative of this, which is just 1, right? The derivative of x is 1, the derivative of negative 1 is 0. So then we substitute in, we plug in, and we get 2 times 1 plus 2, and that gives us 4. So when we go through this, we also did with simplifying, we also got 4. So that's L'Hopital's rule. Now normally, if you could simplify it this easily, I would stick to simplifying. But L'Hopital's rule works anytime it has that indeterminate form of 0 over 0. So we're going to take some other examples that you can't simplify that easily and show how that works as far as using L'Hopital. For example, if we have 2 e to the x minus e to the negative x over x, and we plug in a 0, what happens is we get 2 times e to the 0 minus e to the 0 all over 0. Okay, well, e to the 0 is just 1, so this is actually 2 times 1 minus 1 all over 0. Okay, so then we have 2 times 0, which will give us 0 over 0. So there's our indeterminate form. So it didn't work, but we know because it equals 0 on the top and the bottom that we can use L'Hopital's. So to use L'Hopital's rule, we take this, and we now are going to take the derivative of each of the functions. So we're going to move down. I'm going to kind of give a little, we're going to take these functions right here, and instead we're going to rewrite it as the limit as x approaches 0 of the derivative of this. So the derivative of this would give us, first of all, the 2 is just there, right? 2, kind of like if it was 2x as the outside function. 2x, the derivative of 2x is just 2. Then we multiply by the derivative of the inside function. So the inside function, e to the x, the derivative is e to the x, minus the derivative of e to the negative x is e to the negative x, but we have to multiply by the derivative of the negative x, which would be a negative 1. So we get a negative e to the negative x. And then we get the derivative of x is 1. Okay, so now we can go through. I'm going to just simplify this a little bit more. So you can see, so we have the limit as x approaches 0 of 2 times e to the x plus e to the negative x all over 1. So then when we plug in that 0, we get 2 times 1 plus 1 and all over 1, which gives us 4. Okay, that's just a coincidence that that one equals 4 as well. Okay, so that the limit as x approaches 0 is 4. Now, what does that mean? Just a little reminder on what we're actually talking about here. What that means is that when this function here, when it approaches x equals 0, the y value that goes with it is 4. Now, it is undefined at 4, but if it were to go on continuously, then it would equal 4 at that point. So it's kind of telling us where it would be continuous, where it would follow through. Okay, and hopefully we can go back and talk a little bit more about limits during class. And yeah, so let's just write one more definition of L'Hopital's rule here to kind of help understand hopefully what it means and how to use it. Okay, so if the limit is 0 over 0 or infinity over infinity, then we can use L'Hopital's rule, which says that the limit as x approaches a number of your two functions divided by each other is equal to the limit of the derivatives of each of those functions as well. Okay, we'll talk about it more in class and go through your assignment.